Hello students, this is video number 3 on capacitors. Today we are going to learn some more very interesting problems on capacitors, on combination. These are the symmetric connections and some Houston bridge connections and so on. So I am D.N.Thatoi. Welcome you all to my new YouTube channel Physics Sketch. So these are the problems we are going to solve and shown in the figure, and then these are the formula again. I am repeating for you for your reference. These are the parallel connection C1 plus C2 plus C3. Again series connection, two series, that is series connection 1 by C1 plus 1 by C2. So now net resistor capacitance is C1 C2 by C1 plus C2. Similarly, if the n identical capacitors are connected in series, in series connection net capacitance decreases, so that is Cs is equal to C by n, and in parallel connection capacitance increases, so net capacitance becomes Nc. Same thing will be repeated. This is the basic formula on capacitors, and these basics, so we will try all type of combination to bring them to either parallel connection or series connection. But in addition to that, so today we will be learning about some special type of connection or special type of analysis, that is symmetric connections, so how to analyze the problem, and Houston bridge connection, what is that Houston bridge connection, and it is a balanced Houston bridge or unbalanced Houston bridge. This type of connections we will be discussing today. So now first let us come with the combination of capacitors, the problem number 1 that is given in the question number 1. Look, these are the two capacitors connected in series. Simplest, these are the two capacitors connected in series, and the capacitor, this is equal to 3 microcoulomb, this is equal to 6 microcoulomb. Then you have to find out what is the net capacitance between the point A and B. So as usual, so now to get the net capacitance between A and B, let us connect with a battery. So now for this analysis, now the amount of charge that is going here, let the amount of charge going here is Q, so it will be plus, it will be minus, and same charge Q will come to this point, that will be again plus, and this is minus. So this is the plus side, so all the left side will be plus, this is the negative side, all the negative side will be right side will be negative, and same charge will flow to this as well as this. That's why they are called series. In series connection, same charge will follow to all the capacitors, then it is called series connection. So here the net capacitance according to the formula, what is the net capacitance between the point A and B? So the net capacitance is equal to C1 C2 by C1 plus C2. If two capacitors are there, always use this formula. Otherwise, series connection formula is 1 by C is equal to 1 by C1, 1 by C2 plus 1 by C3 and so on. So here the net capacitance is equal to 3 into 6 divided by 3 plus 6, and it is equal to 18 divided by 9, that is equal to 2 microfarad. So the capacitance of the first problem is 2 microfarad. Series connection. Series connection means same charge will flow to all capacitors. Another condition of series I am showing here. Let's say this is a capacitor. This is a capacitor, this is a capacitor, again this is a capacitor, again this is a capacitor, then again this is a capacitor, this is B point, this is A point. Though they seems to be parallel, let's say this capacitor is not there. See, though they are seems to be parallel, but same charge Q will flow to this, again to this, and it will flow this way, and it will flow this way, then again it will flow this way. So since the same charge will follow to all capacitors, so C1, C2, C3, C4 all are in series connection. So again you just recall that or you try to understand. So what is the condition that the capacitors are in series? The same charge will flow from this to this. There is no other path. It will again go to this one. Same single path. It will go this way and come to this. If all the capacitors are in series and all are C, suppose the net capacitance series will be how much? C dash is 1, 2, 3, 4, 5. So net capacitance will be C by 5. So please note what is the connection and how to decide whether they are series connection or parallel connection. Question number 1 is over. Now come to question number 2. Now in question number 2, there are again 3 capacitors given here. Now this is a, let's say, is a, with the combination is from the center, 3 capacitors I have taken. This is capacitor 1, this is capacitor 2, this is your capacitor number 3. There are 3 capacitors. Let all capacitors are same value, C. So this is the center, name of the center is A, name of this point is B. So it is required to get the net capacitance between the point A and B. This is my question. Look here. To get the net capacitance between the point A and B, who is A? A is the center of the circle. Who is B? Now B is the any point on the circumference of the circle. Okay. So B may be this point, B may be this point, B may be this point, because on the circumference is a conductor. The circumference is a conductor. I told you, in a conductor, the potential here, all are same. If this is B, this point is B, this point is B, this point is also B. So now, if this is the case, then what to do? Let us redraw them. This is the point A is the center. Another point is B is the any point on the circumference, because in the circumference only a conductor. So all capacitors are going from A to B, A to B, A to B. So all the capacitors A to B. Another capacitor A to B. Another capacitor A to B. So the net capacitance of the system is how much? C dash is equal to 3C. So the 3 capacitors are in parallel. So this is how you have to imagine how to redraw the diagram. What is the concept of redrawing? Then how to get the new capacitance, the equivalent capacitance. So this is over. Please note down, question number 2 is over. So another case, the same question number, this also I am giving a, so for you as a homework, you can note down. So let the capacitors are like this. Let the capacitors are like this. I am drawing here. Please try to solve by yourself. Now this is the point. So these are the connected to this point. So these are the now capacitors. These are the capacitors. And B is a point on the circumference. A is the point on the center. So what is the net capacitance between the point A and B? All capacitors have capacitance C. How many capacitors? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So net capacitance will be how much between the point A and B? There are 12 capacitors. There are 12 capacitors and capacitance each C. All capacitors are C value, same value. A is the center, B is the circumference at any point on the circumference. So you have to find out what is the net capacitance between the point A and B. Same, take a point A, that is center, another point B on the circumference. From the point A, 2 lines are going. After reaching here, so each line again going to B, So please try to solve this problem. This is the question number as a homework for you. Okay. Next, please note down. Okay, please note down this one. Now come to question number 3. This one. So in this connection, so look here, the questions are given. This is the point A, this is the point B. So now this point and this point. So here there is a capacitor. Here there is a capacitor. So here there is a capacitor. And again here there is a capacitor. So all capacitors are C. So you have to find out what is the net capacitance between the point A and B. This is your question number 3. So this one is over. This one is over. Now this is the question number 3 we have to solve. So in this connection, to get the net capacitance between the point A and B, so how to start? So are you able to follow that this is a conductor, this is a conductor. If this is a conductor, I told you If the name of the point is A, name of the point is also A. Name of the point B, so this point can be given any other name, B say. So always you see which points having no capacitor, nothing. So all the points you give the same naming. If this is A, this is A. Now the problem is reduced to simpler one. Look, this is the point A. This is the point B, and P is any point in between. Let us note down A, P. Now a capacitor is A to P. This capacitor A to P. So let us connect it A to P. Another capacitor is between A to P. This is also between A to P. Connect it. Another capacitor is from A to B. So A to B. This one. This is A point. This is B point. This is A point. This is B point. Here. Another capacitor is between B to P. So this capacitor is from this to this. So now this point is P. This all capacitors are capacitance C. Now this diagram is reduced to a simpler diagram where you know parallel combination and series combination answer. Now in this case we can calculate the net capacitance will be how much? Look here. Now in this is the C, this is C. So these two are in parallel. If these two are parallel, so net capacitance will be 2C. Now let us again redraw. This is the point A. This is the point P. This is the point B. A to P, 2C. So let us connect one capacitor, that is equal to 2C. Another capacitor P to B. So let us connect one capacitor P to B. Another capacitor here. So now this is also, let the point is P, let point is C, this is C. Again, these two capacitors are now in series. If these two capacitors in series, then you connect, this is the point A, this is the point B. So now the top line the capacitor becomes something, bottom line capacitor becomes something. This is 2C, this is C. What is the net capacitor? This one, that is equal to 2C1 into C2 divided by C1 plus C2 formula. So that is equal to 2C square by 3C, 2C by 3. So this is equal to 2C by 3. This is equal to C. Again they are parallel. So the net capacitance between A and B is 2C by 3 plus C parallel. It is coming to be 3 LCM. It will be 5 by 3C. That is the answer to the question number 3. So this is the combination of the capacitors. So please follow again what I have done. Now this is the point A. So I have given the point A also because there is no connection. No connection here because no capacitor, no resistor, nothing. So if potential of this point, potential of this point are same. A from A to P, two capacitor. P to B, one capacitor. From A to B, direct. These two capacitors are in parallel, 2C. This is C, this is C. This is P point, this is P point. This is A to B directly, So 2C and C series. Series means C1, C2 divided by C1 plus C2. So this is equal to 2C by 3. So this is equal to 2C by 3. So 2C by 3 and C parallel. So this is 2 by C and C plus C is equal to 5C by 3. Answer to this problem number 3. Now come to question number 4. So these are all capacitor connections. Some problems are direct parallel and series, and some problems you have to apply some trick, some ideas, and other problems will be that is Houston bridge connection will be coming now next onwards. Okay. Now come to question number 4. So in question number 4, the capacitors are given like this. Look here, these are the capacitor, these are the two capacitors are connected like this. Okay, so here there is a capacitor. Okay, now another capacitor is connected like this, and these wires are connected here, and this point is B, this point is A. So you have to find out what is the net capacitance of the system. So now gradually things are becoming more easy. So you know if this is the B point, this is the B point, this is B point, this is B point, this is B point, this is B point. This is A point. This is A point. Very interestingly, you can reduce the problem easily. So because this is B, now all the lines are same B because this is conductor. This is B, this is also B because nothing is there in between. This is B means this is B. So how many capacitors? 4. They are connected between which 2 points? A and B. So look here, one is A, another is B. Between the point A to B there is a capacitor. Let us connect A to B. This one. Another capacitor between A to B. Yes, connect A to B. Then this capacitor is again between A to B. Look here. That's why you everywhere you write B or A, B or A. There is no other naming. So this is A, this is A. So that it will be not confusing. A to B, this one. A to B, this one. Then another capacitor left, that is equal to B to B. So already we have discussed if a capacitor is connected from B to B. So that is, it does not matter. It does not matter. This capacitor has no meaning because it is connected in the same point. So the capacitor should be either connected to A to B, then only you can able to calculate the capacitance. So this capacitor is started from this point and again it is coming to the same point. So this capacitor is meaningless. So the net capacitance between A and B is obviously they are parallel. The answer is 3C. So answer to the problem is 3C. Please note down the net capacitance between this point A to B is 3C. Look, the idea is if this is B, 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 this is A, this is A, this is A. So then the problem is redrawn and you will be getting the answer. Next question. Next question will be on some symmetric connection. One side is symmetric to another side. One side is image of another image, another side. So if this is the case, then how to solve the problem? Look, this is my first problem on symmetric connection. Look here. These are the capacitors. There are 5 capacitors. They are connected like this. This is equal to C. This is C. This is C. This is C. This is C. There are 5 capacitors connected between the point A and B. Then how to get net capacitance of the system? So here, so you cannot say that these two are parallel. So these two capacitors cannot be parallel. Why? So let me explain. You try to understand. So these two capacitors cannot be parallel. What is the condition that two capacitors will be parallel? These two will be parallel if left side will be connected to one end and right side will be connected to another end. Then this capacitor C1, C2 are said to be parallel. But here this capacitor left side is at one point, this capacitor left side is the same point, but right hand side again they are connected by a capacitor. Instead of this, there is another connection like this in this problem. So it is like this. Then we cannot say these two are parallel. These two will be called parallel if left will be connected at one point, right will be connected another point. Similarly, this side also. Similarly, this side also. Here, neither of the capacitors are in parallel nor them are in series connection. So this type of connection is called Wheatstone bridge connection. Wheatstone bridge connection. So this type of connection is called Wheatstone bridge connection. Please note down things. So time to time you review the video and see and try to understand. This is called the Wheatstone bridge connection. So in this Wheatstone bridge connection, how to get the net capacitance between the point A and B? Look here what I am telling. How to solve the problem? Look. So this is Wheatstone bridge connection. Please note down. Now to get the answer to this question, so now let us first connect a battery. So this is because question is to ask find the net capacitance between A and B. That's why between A and B means between the point A and B you are going to connect a battery. That is the idea. Between the point A and B you are going to connect a battery. That is the meaning net capacitance between A and B. So what to do here? Look here the symmetric. Can you say that this vertical line divides the two parts into two equal halves? Yes. Because if you draw a line here, if you draw a line here, look here. If you draw a line here, this is the line of symmetry. Left side and right side just image of one another. If you draw a vertical line, so left to it, this one, just right to it, same pattern, same capacitor. So this one and this one, again they are symmetric. If they are symmetric, then one can assume that if in this line charge will go X, then if this line charge will go Y, then same X will also again if this, because this and this are two symmetric. If here charge is going X, then in this direction charge will return X. If along this line charge is going Y, then because these two are image to each other, so same charge Y will be going this way. So this is very important part. Please be careful and try to understand why this S, why this is X. Because if you draw a vertical line, the left part is just a image of right part, or right part is just a image of. So image means what? Similar condition, same condition you will be achieving. If here X current, then here will be X current. But obviously it is the input side, it is the return side. That's why if this is X, it will be X. It is Y, it will be Y. Now come to the point. If here X is coming to this point and same X is going to this point, what is the charge coming to this point? No charge will be going this line. If no charge will be going this line, then you have to ignore that capacitor, it is meaningless. Though the capacitor is present here, but this charge is going in this path, this charge is going in this path, and along this line neither charge is coming from top to bottom or from bottom to top. If this is the case, then you have to redraw the diagram with the concept like this. Look here, so one problem I am explaining nicely, then other problem you can solve by yourself. Now these are the problems, and this capacitor has no meaning, so remove it because it is neither be charged, okay, it is not charged at all. So now it will be like this. This is A point, this is your B point, this is C, this is C, this is C, this is C. So now obviously you know these two are series, C and C series C by 2. This is C and C series C by 2. So the net capacitance between this point will be now again how much? So these two will be series. In series capacitance decreases, it will be half, because same value, again it will be half, and these two connections are again between A and B. So the net capacitance between A and B is equal to C by 2 parallel. Add them, C by 2 plus C by 2 is equal to C. So the net capacitance between the point A and B is equal to C. Answer to the problem number 4. So the question number 4, this is your answer. Please note down. Please note down. Okay. So this is very interesting problem. So try to see repeatedly what is the meaning of symmetric. If this is symmetric, the image of symmetric, about which line it is symmetric. So if this is X, it will be X. This is very important. If this is Y, it will be also Y. If this X is going directly to this, what is the use of this line? No use. Remove it. Make a simpler diagram. Then net capacitance is equal to this much. So another point we have to understand here. So I told you, so along this line no charge will flow. So if no charge will flow along this line, because same X will follow this one, what is the meaning that no charge will, though a connection is there, but why no charge is flowing? Then another concept is coming to mind. If no charge is flowing in a path, this is the path. If no charge is going along the path, then potential of this point and potential of this point is same. If I will say potential of the point is P, then potential of the point P, then in the same potential 10 volt, this is a potential of 10 volt. If I will join a capacitor or a ball or anything, so it will not glow, or no charge, no current will pass through, because this point has potential 10 volt, this point has also potential 10 volt. So this is P 10 volt. Let's say this is 10 volt, no current will flow. That means these 2 points are of same potential. If these 2 points are of same potential, what to do? Another method you can solve by using another method. Look here, this method is over, already I have explained. Another way also you can see. Because so many problems are there, either this one or that one, you have to apply. That's why if this point is P, this point is P, and they are found to be same potential. Why same potential? Though here there is a capacitor, but current is not going. So what is the condition that no charge, no current will flow in a path? Obviously, this potential and this end potential should be same. If potential is the same, so why the current will flow? Current flow or charge flow because of the potential difference. So now, if these are the 2 points same, now come to another way of solving. This is the A point, this is the B point. Now this is point P, because this point P, this point is also P, A to P. Then this is again A to P. Then again from P to B. Again from P to B. Now C. Now again you can say that is CC, 2C series. Again parallel. Again CC, 2C. They are parallel. Again A between A to B. Again there are 2 capacitors in series. So net capacitance between A and B will be 2C. So basically half of 2C. So answer is equal to C. Either this way or that way. So answer is not important. Important is the concept, how you are deciding how to solve the problem, and whether the charge will flow the same or different, or everywhere charge will be distributed. This is very important. So this is what called Houston bridge connection, and again this is a balanced Houston bridge connection. So all the information regarding this video, please see time to time, repeat the video and see, so that concept will be clear. So this type of connection is also called balanced Houston bridge connection. Why it is called balanced Houston bridge connection? So I am explaining, that is the last part of this problem. So a Houston bridge is said to be balanced. Look here, a Houston bridge is said to be balanced if so one more thing, a Houston bridge is said to be balanced between A and B. This is called bridge capacitor. This is C1, this is C2, this is C3, this is C4, then this is 5. For balanced Houston bridge connection, so now we can say C1 by C2. This capacitor divided by this capacitor. Ratio of these 2 capacitors is same as ratio of these 2 capacitors. Then it will be balanced. If it is balanced, then potential of this point and potential of this point are same. Please note down. If this by this is equal to this by this, then potential of this and potential of this will be same. Then we can follow the earlier method or this method to solve the problem. This is called balanced Houston bridge connection. Thank you.